All right, today we're going to be discussing lesson 11.3, which is similarity within right triangles. And we're going to have a special situation within right triangles and then see what transpires from there. First, we're going to look at this proportion here. Remember, a proportion is when you have two ratios that are equal to each other. And this is a special proportion because you notice here that in the denominator of the first ratio is an x, and there's also an x in the numerator of the second ratio. So therefore, this has a special name to it. In this proportion, x is said to be the geometric mean between m and n. And we know if we have proportions, we can solve them. To solve, we cross multiply, and so we would get x squared equals m times n. And then to solve for x, you could take the square root of both sides and have plus or minus the square root of m times n. Now realize we're in geometry here and we'll be dealing with lengths quite a bit. So for our circumstances, we will be using a plus sign when we work with the geometric mean. And we're going to see that term later on. So here's just a couple quick examples. Find the positive, so it mentions there the positive geometric mean between each pair of numbers, 3 and 27. So if we want to find the positive geometric mean between 3 and 27, we want to put a variable there in the denominator of the first and in the numerator of the second. Those are actually called the means positions, so that's why it's called a geometric mean, or one of the reasons. So that's the means positions. So we put a variable there, and then we cross multiply. We get x squared equals 81, and we take the square root of both sides, and it did say, again, find the positive geometric mean. So the positive geometric mean is 9. The next one, same idea. We'll put a variable in the means position, and the 6 and the 9 in the other positions. Now, honestly, it doesn't matter if the 6 goes first or the 9. You could actually have the 9 up here and the 6 down here. So go ahead and cross multiply. X squared equals 54. Take the square root of both sides. If you remember how to simplify the square root of 54, that's 3 root 6, which is approximately equal to 7.35. So that's geometric mean. We'll be using that a little bit later. So here's the special situation we're going to talk about. We're going to start with a right triangle, and notice here we have this larger right triangle, triangle ABC, and we have an altitude drawn from the right angle. So I'm going to refer to this bigger triangle as the original triangle. So we have an altitude drawn from the right angle down to the other side. Actually, it's the hypotenuse, and we have two more smaller triangles formed. So what I want us to notice here, here's the one smaller triangle, here's the other one. We're going to recognize something that happens here. So there's the first triangle, the left one. Here's the other one, and we're going to spin that around. And we're going to notice here, so I want them all the same, facing the same way. As we look at these, we notice that when we dropped this down and spun it around, this is angle A. It's the same as this angle here. Here's the right angle, which goes along with where D is. So that's that angle there, and then here's C. So this is triangle A, C, D. Over here, maybe you can figure out which triangle this is, what these names are. Here's our right angle. So that corresponds with this one, so that point will be D. So we look at this one, B, that's going to be B, and then this last point here is going to be C. So we have those two smaller triangles. Now, what we can notice here is that these triangles are going to be similar to the original triangle because we have angle, angle. We have angle A congruent to angle A, and then the right angle D congruent to this right angle up here, angle ACB. Same concept over here. Angle B is congruent to angle B. and then the right angle is congruent to the right angle. So those three triangles end up being similar. That's the first thing that we learn here, the right triangle altitude theorem. The altitude to the hypotenuse of a right triangle separates the original triangle into two triangles that are similar to the original, and similar to each other. So that's the first theorem. And this is the theorem that we use to prove the other two theorems. So here's an example, and kind of like filling this in, if the altitude is drawn from the right angle to the hypotenuse of a right triangle, then the two smaller triangles that are formed are similar to the original triangle and each other. So that's what we just mentioned. And then we have an example here, state the similar triangles. Order of letters is important, just like in congruent triangles, order of letters is important. So let's go ahead and start with the largest triangle, and we'll go in alphabetical order. Largest triangle is RST, RST. So what is going to be similar to triangle RST? Well, in this top triangle here, let's look at this one. Notice over here we started with R, which was the right angle, so we need to start with the right angle here. So that's going to be W, so triangle W is going to be the first letter. Then we went to S, this angle up here. Well, angle S is congruent to itself, so we should do W, S, and then we'll finish with R. And then for the smaller triangle, once again, we start with a right triangle, or right angle, angle R. So we need to start with the right angle over here. So we start with W, and then we went to S. Well, this one doesn't have an S, but notice S is the acute angle. Another thing we can notice is that it ends in T, so that this angle we need to end in T. So this will be WRT. And those are the three similar triangles. Let's move right into the next theorems. This one says the altitude geometric mean corollary, and remember a corollary is really just a theorem that's easily proven from another theorem. Now I want to point out several things here first so we can kind of develop this. I feel like this is kind of the best way to look at this. We have our original triangle, triangle ABC, and then our two smaller triangles. So we're going to kind of mark all the corresponding parts here. So H, here's H, that's our altitude. We use H because it's the height there if we're looking at the hypotenuse as the base. So H, so notice H shows up here, that's segment CD. So H is in both of these triangles. And then we're going to go to the different legs. We call this leg A. This is A because it's across from angle A looking in our original triangle. Notice that's segment CB, which is the same one as this down here. Next, we'll look at the other leg. So here's angle B, across from that is side B. And notice that's down here in this triangle when we flipped this one and rotated it. Next, this hypotenuse, or this altitude split the hypotenuse into two parts. X, we'll call this side X, which appears down here. There's X, it was segment AD, and then Y is over here, segment DB, that's segment DB. And one thing I want to also mention is the whole thing down here we call segment C, that's the hypotenuse. So this is called the altitude geometric mean. So we want to use the altitudes or the altitude to come up with a proportion. And so you see here we're going to use the two smaller triangles to write a proportion using H, which is the altitude. All right, so we'll start with this triangle here, and I'm going to kind of be choosy about this. I'm going to do X over H. So this X, so what corresponds to X? This H corresponds to X, so X over H. And then we're going to do equals, and we're going to use this side along with Y, so equals H over Y. So we're going to put this proportion kind of in a word form. Notice x and y were the segments of the hypotenuse after we drew in the altitude. So the altitude split the hypotenuse into two parts, x and y. So I named x segment 1 of the hypotenuse. I named y segment 2 of the hypotenuse. So notice here, segment 1 of the hypotenuse, over the altitude equals the altitude over the segment 2 of the hypotenuse. Now we notice here altitude is in this means position. So in words, we can say that the altitude is the geometric mean between the two segments of the hypotenuse. So the altitude of the hypotenuse of a right triangle divides the hypotenuse into two segments such that the length of the altitude is the geometric mean between the lengths of the two segments of the hypotenuse. So that's very wordy. I actually prefer just knowing and remembering this proportion here. So if you're working with a right triangle and the altitude's drawn in, and we either know the altitude or want to find the altitude, we're probably going to use this theorem. So here's an example, but first let's fill this in. If the altitude is drawn from the right angle to the hypotenuse in a right triangle, then the length of the altitude is the geometric mean between the lengths of the two segments of the hypotenuse. So that's what we just mentioned. So looking at this example here, it says find x. So x is the altitude that's drawn from the right angle to the hypotenuse. So we know, so I have a little card here. Here's going to be our two theorems, but here's the top one. We know the altitude is the geometric mean between the two segments of the hypotenuse. We can write that little equation. Segment 1 of the hypotenuse over the altitude equals the altitude over segment 2 of the hypotenuse, and we're going to fill that in. So I usually start with the proportion and I start filling in. So x is going to go into the altitude positions, and then I mentioned before the 9 and 4, they can go, one can go on top, one can go in bottom. So in this case, I put the 9 up there. So the x is in the means position, and then 9 and 4. So we cross multiply, and we take the square root of both sides, remembering this is a length, so we don't need the negative. So x is equal to 6. All right, our next theorem has to do with the legs. And when we talk about the legs, we're talking about the legs of the original triangle. So in this case, we need to look at two different things. So we're going to use the original triangle with each of the smaller triangles to make proportions. So let's first start with using the left triangle over here. So we're going to use the original compared to the left triangle. So what we're going to do here is we're going to start with the hypotenuse. This hypotenuse compared to this leg. So we have the hypotenuse over its corresponding side. So notice this is the bottom part of this big original triangle, and here's the bottom of this triangle. So hypotenuse over leg equals leg over, and what did that correspond with? Well, that corresponds with x. And then what we can do is we can look at the original triangle compared to the right, and this means the one on the right. And we're going to do the same idea there. We have the hypotenuse, so this side over the leg is going to equal the leg, so this side up here over this value y. And now we want to take a look at each of these, and we can realize that there's a little bit of a pattern here. Notice there's the hypotenuse in both of them. A leg is the geometric mean here. A leg is the geometric mean here. Remember, that just means it's in that bottom of the first fraction and top of the second fraction. And then this x and y, well, those are parts of, if you go back to the original, they're the two parts of the hypotenuse. And the nice thing is x, this length x, is adjacent to the leg that we're talking about. And then y over here in this one, y is adjacent to this leg here. And so we can kind of combine these I know this is a little wordier, but we always had the hypotenuse in the top left, and then a leg here, and this is the same leg. So leg, leg. So the leg is the geometric mean between the hypotenuse, and this is how we describe the other part, the segment of the hypotenuse adjacent to the leg. And there it is in words, the altitude. To the hypotenuse of a right triangle divides the hypotenuse into two segments such that the length of each leg, so we're talking about the leg, is the geometric mean between the segments of the hypotenuse adjacent to the leg and the entire hypotenuse. And so once again, we can fill in the blank here. The altitude divides the hypotenuse into two segments so that the length of a leg is the geometric mean between the hypotenuse and the segment of the hypotenuse adjacent to the leg. So we use this theorem when we're either looking for a leg or want to find a leg. In this case, or we know a leg, sorry about that. In this case, we have M here. So we're looking for this leg M. And so here is our theorems. We're not dealing with the altitude. We don't know the altitude. It didn't ask for the altitude, so we're not using this proportion. We're going to be using this one. So we see that the leg, we're going to use this formula. The leg, well, that's M, so that goes in the geometric mean spot, M and M. And then we have to be careful here. It's the hypotenuse. Well, the hypotenuse is this whole length. So 4 plus 9 is 13. So that goes in the hypotenuse. And then how do we know if we choose 4 or 9? Well, we choose the one that is adjacent to the leg that we're talking about. So we use 4. We cross multiply, m squared equals 52. We take the square root of both sides, and we get m equals, if we simplify the square root of 52, it's 2 root 13, which is about 7.2. So here's another example. It says find the value of each variable. Well, we have h, t, and r here. So let's go ahead and look at h. I shouldn't have put that up there yet, but notice h is, so let's go back, h is the altitude, so we're going to want to use this one. So h is going to go into these two spots, and then the 4 and the 16 can go into these two spots. It doesn't really matter which one, but I know you can't see it, but here we have 4 is the top and 16 is the bottom right. So we have 4 over h equals h over 16. We can cross multiply. H squared equals 64, and we take the square root of both sides, and we get h is equal to 8. All right. What else do we have here? Well, we have a leg, and this is a leg. So we want to find the two legs. It doesn't really matter which one we find first, but just realize we're looking for the legs, so we're going to use this formula right here. And so to find t, that leg is going to be the geometric mean. It's here and here. T is the geometric mean between, and this is, again, it doesn't matter which place you put them. I have hypotenuse would normally go here, and the segment would normally go on the bottom right, but they have it switched here, which is fine. So hypotenuse and the segment of the hypotenuse adjacent to that leg. And then once again, we cross multiply, t squared equals 80. You take the square root of both sides, you're going to get really close to 9, probably 8.9, or if you simplify root 80, you get 4 root 5. And then same idea for the last one. We have the leg in the geometric mean spot. Here's the hypotenuse. So here's r. We have the whole hypotenuse compared to the segment of the hypotenuse adjacent to the leg that we're talking about. We cross multiply. We take the square root of both sides, and we get 8 root 5, or you could use a calculator to find its decimal approximation. So that's how you use those theorems. Make sure you know them. Again, you can know the ones that are written out in words, or if you know these two proportions, it's going to be very helpful.